I would like to say a few words maybe on this particular program. So Ricarda and I started this program on quantum and physics-based machine learning, and we're both very excited about this. In fact, I think there are several good reasons to connect physics with machine learning. I can think of at least 3 reasons. So one is that actually traditionally physics has been very influential in providing technology to machine learning. So I'm thinking about all the approximate inference methods that have been used in probabilistic modeling and Bayesian modeling, using methods from statistical physics such as Monte Carlo sampling and the variational methods and belief propagation methods such as those. They all have a tradition in physics. So there's a great inspiration from physics for machine learning. Also think about encoding invariances using group theory, or using information geometry, using Riemannian manifolds, and so there's a great inspiration traditionally, and this already goes back, I think, many years, at least about 40 years. So also the Hopfield model, of course, is a great contribution from statistical physics to the machine learning community. So that's one reason. So the second reason is the reason actually maybe that this is now this new fashion of the deep learning, which has of course resulted in a lot of applications in all kinds of fields, not only in but also so in society, but also in science, and also in physics and chemistry. So there are spectacular results using neural networks to describe ground states of quantum systems. And of course, also in chemistry, in quantum chemistry, there's a lot of application of machine learning methods in that direction. So that's the second reason. The third reason, I think, is also maybe very important. Is in fact that we are reaching the end of the CMOS technology, and it's really pushing to the limits, and we are in need for novel hardware designs for computing. And since the particular nature of machine learning there's an interest in special purpose hardware development, bypassing the CMOS and going maybe directly to the atomic or very low, very small scale level, where you can use physical properties of the materials directly in the advantage of some sort of exotic type of computing. And that's the third line coming here together. And I think we have examples of all these 3 types of research here in this meeting. And I'm very excited that we have now this program. So we started initially, this was supposed to be a live meeting in Tübingen, just with the fellows, and then extended to some more people. Now with the online, of course, we cannot have this meeting in such a way. Therefore, we make do with the online medium. But as a side effect, actually, we got a lot of interest in this meeting, and so there is probably we get now a wider group, a larger audience in this way than we could have hoped for with a live meeting. So there's also some pluses on this side. So with that, and also on behalf of Ricarda, I would like to welcome you very much to this meeting. And I think we should start with this first session. And each session is chaired by a session chair. And so I give the word to the first session chair, which is Vedran Dunchko, who is one of the fellows in our Alice program. Vedran.